All right, so anyway, so yeah, the homeworks were good. Well, the one group that you guys, anyway, there are the answers were in the back, if you noticed that, but the group that let me know that got a 90 and everyone else got 100, so it doesn't matter much, you know, so I'm just giving whole grades, so it doesn't make any difference. It's kind of odd that like, no. I think, I don't remember what you guys got wrong. I think you just missed answering some parts, something like that. But anyway, I've already kind of gone through that twice and the answers are there, so it's probably not worth going through again. Right, I wanted to, any questions on that thing though? I mean, the homework, but yeah, I wanted to, I missed some little bit about this. I like this little thing about scattering, the interference pattern, the Moiré fringe. So anyway, so there's one other thing to look at with this. Like, so this would be like diffraction, and your crystal spacing would be that spacing between the fringes, right? So you could draw a crystal like this. That's a simple cubic in a 2D projection, right? But again, this is like a 3D technique. So if you take your 2D crystal, so you have a perfect crystal like a diamond, and you throw it into the beam. Let's see, I should be able to move this thing. It's not letting me. It's like that. Let's see. There's something weird about this. I think I put it into some weird mode. It should have a handle on it, right? I should be able to move these things.
You have to enable editing, I think. Maybe.
Where?
Up in that.
Top, that yellow bar.
Oh, thanks. See, like, that's the problem with my brain. It's like, I don't see. All right. All right, thanks. All right, just go away, Microsoft. All right, so you have your crystal. Oops, the crystal, right? So say this is a piece of diamond or diamond ring, and you have a, oops, I didn't want to do that. So I wanted to, I'll rotate it. So you take your diamond ring and you have a monochromatic X-ray. It's like a normal X-ray source. Then you throw the diamond ring into the X-ray. Well, the fringe pattern has to be like right on the plane, right? So you'll get, if you just throw a diamond ring into an X-ray beam that's monochromatic, you'll get nothing out. You won't get a diffraction pattern, right? So in order to get it, you'd have to rotate the diamond ring until the crystal planes line up perfectly, right? So, and only under that condition do you get the diffraction event, because it's the only time that the material would be on it, right? So there's two ways. So that's the basic beginning problem, right? You won't get any diffraction out of it. See, it isn't like a microscope where you see it. You only see it when it's lined up right. Right. So there's two ways around that. You could take the diamond ring and grind it into a powder. Then you would have all possible arrangements of the crystal, and then you would get a diffraction pattern from it. So that's called a powder pattern, right? Then, or you could take the diamond ring. That's not, like, you probably don't want to do that. Or you could take the diamond ring and put it into a rig that would spin it around, right? So you could get at least all, but that only gives you all the planes on one axis, not in 3D space. Somehow you could probably spin it in 3D space too, but no one does that because it's kind of hard to do. The other thing you can do is, instead of saying you have monochromatic, just let white radiation come in, like just any wavelength, and that broadens like the window over which you can get this interference pattern. So not just one spacing of the brown things, but all possible spacings of that within a reasonable whatever you can produce. And then you will get the pattern no matter if it's perfect crystal, right? So that technique is called the Lowy technique. It's a Lowy method. So you come in with white radiation, And that was the original, von Laue was the original diffraction guy. He worked as a medic in World War I, and they had just invented X-rays, and they realized they could see bones like when they broke. And then he just started sticking things into the beam, and the X-rays weren't monochromatic. They were just basically a light bulb. Like you have a filament, high voltage drop, and the electrons hit the metal, and you get Bremsstrahlung radiation. It's white. It's kind of like broad spectrum. So von Laue figured out how to sort out, and still today, like if you want to do, well, if you're doing semiconductors and you do this kind of Laue experiment where you come in with white radiation, you want to, when you make a semiconductor chip, it has to be like a perfect crystal plane that you're working on, like the 110 plane of silicon, right? That's got to be the top plane. If you ever see a silicon wafer, I have some in my office, but one side is it's round, and then one side is flat, and that flat is where the 110 is. You know, and the face, I guess, is a 111, and the nib on the side is a 110, and from those two planes, you can figure out the orientation of the crystal. You know, and each one is a perfect crystal. So anyway, the point of that is you find that out by sticking it in a Laue camera. So you have no, so a normal X-ray tube is going to have this white radiation. You put in a nickel filter to block out the copper K beta radiation, which is a dominant problem. So you have alpha and beta. Those are emission lines from the electron bands, you know, have energy, and then the copper, which is the targets, electrons go and fly against the copper, the electrons fly out, then they come back in and release these monochromatic bands. So the K alpha, K beta, it's the K orbital of the copper, and it's K alpha and beta, the two prominent ones. Forget what it is. One goes, anyway, those bands are split into different energy levels, and then like one is like if it falls back to the same energy level, and the other is if it falls to a different energy level. So alpha and beta are the two dominant wavelengths. So the alpha is 1.54 and beta is like 1.7, I think. So you want to get rid of the beta, so you put nickel, it shields it, it absorbs it. It's got an absorption band that takes care of that. Anyway, so that's like the cheapest X-ray camera. So that's one thing. And then, so the orientation matters. Like if someone asks you, like, I have a monochromatic X-ray source, I stuck a diamond ring into it and I got nothing out of it. Why? And the reason is, like, it isn't just going to come out. You have to have it perfectly aligned. So you'd want to rotate the diamond ring or something to get it. Then the other thing is, like, so you can draw, instead of drawing the waves like this, then you can draw these lines, right? So you have the plane, right? It's the crystalline plane. Then the D spacing is normal to that, right? That's the thing you're measuring. So as far as the orientation of a plane, like you have the normal, that's the orientation of a plane, right? And you're coming in with the beam, and it's going to diffract from that plane. You get this fringe pattern. It looks just like reflection, right? It looks like, so they call the X-ray peaks reflections, even though they aren't reflections, because if I just throw a diamond in, I get nothing. If it was a reflection, you'd get something, right? So it acts as if it's a reflection off the crystal plane, but it really isn't, right? So that's called the specular analogy. Speculum is like Latin for mirror. So they call it the specular analogy. And then it's also called, these are called reflections, the diffraction peaks. And the geometry of it is, so you can get rid of the wave altogether and just have this geometry. So you have your beam comes in, it comes out at theta, and this is the orientation thing is theta by 2. It's half theta. Or you call the reflection coming out at 2 theta, and then the angle would be theta. So in diffraction, they call it 2 theta. The angle between the incident and the outgoing, and the angle that you're actually working with is theta. And in scattering, they call the angle coming in is theta, and the thing you're working with is theta by 2, right? And it's just for no particular reason. That's just to make it confusing. And the orientation that you see, so over here, you're going to have a detector, say, like it could be a flat detector, like a CCD. You pick up the beam over here. So if you see something that goes down, you know, the normal to the plane is down. So the directions in this, so it's inverse, big things are small. So infinity is 0. Right? So you can see infinity, it's at 0. And the orientation is 90 degrees. It's the normal to the thing that you're looking at. So if you want to see something that's pointing over there at infinity, you look over here at 0. Right? So the space of looking at stuff in diffraction is called inverse space, and the orientation of things are all orthogonal, or 90 degrees from each other. Right? So that I didn't talk about, but I thought that was kind of important to mention. So anyway, so this little thing can give you a lot of, that little thing about the Maury fringe can give you a lot of information if you want to look at it. And it's kind of simple and consumable level of information. So that's one thing. So then, so I went through kind of radius of gyration, just like superficially, more or less. But anyway, so Dubai, again, like during World War II, let's see, we can open this somewhere. Open link. So this is Dubai's collected works, like from the 60s, I guess 54. That's Dubai. Dubai had this problem. I mean, there's a lot of stories about Dubai, but he got out of Germany, went to Cornell, you know, and then discovered a lot of different things. Anyway, he also like was working in Berlin during the Nazis. So people say that he was a Nazi, but he left. It's a little bit hard to say, but there is some kind of Nazi thing with him that people talk about. Anyway, this was done for the US war project. You can see the rubber preserve company, 1945. So this was held as a secret document, even though it's just like how to do light scattering from polymers in solution. So this is his derivation of that, of the equation for a polymer. Like I said, this is the equation for a polymer chain in solution to get the scattering pattern. So I'll go through that. Anyway, the link is there to that if you want to read it, but here. So anyway, this is about correlation functions. Okay, so the idea is this. Go over to .pm. So if you see, you have the chain, and then it goes to n and starts at 1. And you're at some point, it goes to capital N, say, you're at some point n in it. Right, and then you have a coordinate system like that. And you can have a vector, like a big vector R goes to n, and there's some other point m in the chain. So you go to that point n, and that has Rm. Then the distance between these two is like Rm minus Rn. Right, that's also a vector. These are all vectors. And then you can go and say, if I'm at n, then I'm going to go out distance r. What's the probability of finding some chain there? Right, so if it's 1, it's 100% probability. As you go out, it kind of drops. All this, you know, because of the so if you calculate that mathematically, you say that you have some vector r minus that vector, and then you say when that thing equals 0, then you want 1. So that's what this del thing. So del of 0 is 1. Del of anything else is 0. It's called the del operator. And so it's kind of useful for doing this kind of calculation because it lets you have an on-off switch to say something worked or not. And then if you wanted to sum that over, so for a given r, you'd have g of r, and you want to sum over all possible places on the chain of this thing, this argument, this del thing. Right? And then because you have that n, and that gives you some kind of function that talks about how the density of the thing's distributed in space. Right. And then if you wanted to, right, so that gives you this function. This guy, right? It's a sum from everything, going through everything on the chain, divided by n to normalize it. It said n here, should have been m, because this is for n. Then if you wanted to, so that would be just one point, right? So, so that would depend. Like we started here, it would be a different function than if you started there, right? So you want that averaged over the whole thing for some reason, so that to get what's called a correlation function. So it's how density correlates in space. So it's a pairwise density correlation function. You have 2 points of how they correlate with each other. So then you're going to do like sum of that over all n's. It should be n. Do that over all n's. So then you have a double sum, right? Which looks just like the double sum that we used to do the race gyration. So you have this double sum m and n over this coil, and it's kind of got almost the same argument in it. Like you got this distance is what the thing's going to be. So it means that this r minus n thing is going to give you like the race of gyration. You know, like that double sum over r is going to give you the race of gyration. But we're not getting the race gyration, we're getting this correlation function. It's like how does mass correlate in space with itself? It's got the same 1/2n squared prefactor, this thing, right? And it's got kind of the same double sum. So like I said, everything you're going to calculate in Polymer is going to be this double sum, which ends up being a matrix. Oops. Where did that Debye thing go here? Yeah, so this thing's going to end up being this matrix because you have n and m and they go to capital N, right? So you're going to end up with the same matrix thing. So everything's going to be matrix math if you want to talk about these mathematically. Let's see. So anyway, let's see here. This guy, right? So anyway, so we have that sum that gives you this G of R. That's the correlation function for a Polymer chain. That's like reflects the structure in real space of the thing in kind of a weird way, in the way that so when m equals n, it's 100%. So the thing's going to be 1, right? And then as you go out for bigger distances r, you got to. So sorry. So it's going to be 1 when r is 0. So when n equals m, that's going to decay down. So this is this G of r correlation, the binary pairwise correlation function. And then it's going to decay down somehow. It's going to go to 0. It's going to decay down, and then it's going to truncate to 0 when you reach L, contour length, and LK. Right? So it's going to look like, kind of like we were talking about the probability of to get, we had the probability to find the chain was a NL exponential NL squared, the Gaussian thing, R squared, this thing, the Gaussian bell-shaped thing. It's something like that, but it's not Gaussian. So it's just this correlation function thing. So anyway, so we can calculate that with this double sum mess, right? So this thing's got this kind of, so all right. So the reason you're trying to get this is that it turns out that the scattered intensity is going to be the Fourier transform of that G of R. So the Fourier transform of that weird thing, that correlation function, is this intensity that you measure as a function of Q. Right? And the Fourier transform is exponential minus I q dot r. So q is a vector. So q is the vector from that diagram with the interference pattern, like when we're drawing the arrows and things. Right? And then r is the real space vector. And then times this g of r function. Integrate that from 0 to infinity for r equals 0 to infinity for a fixed value of q. And then you get the I of q out of that. Right, so you want a value of q, like 0.01 inverse angstrom. You plug 0.01 inverse angstrom, and you run through that correlation function of all space from 0 to infinity. This infinity is a little bit of a problem. Right? So you need to, infinity means you have to figure out a way to extrapolate that. But for us, infinity isn't a problem because we end it at L, so we can go to infinity. You know what ends there. Anyway, so this is actually to L. To capital L in this thing. But so anyway, Debye figured out all this, and then in fact, this function, this whole kind of thing, this scheme of doing this, Debye invented. You know, he invented this whole thing. The correlation function is Debye scattering function. So he did all this like in his spare time, whatever. So he was, but one thing is like everything, including Debye screen, like everything that he did involved the exponential function. So it was like his favorite function. It's like, and it's a useful function, but basically it's kind of strange. So it's the same thing, like you have a hammer, everything's a nail. He solves like everything with the exponential function, one way or the other. The Debye screen, like everything's like has to do with that. Anyway, so he's got this thing. So he says, so this is a dot here. Somehow that didn't translate. So q dot r, those are two vectors. And then this is the g of r. He realizes that like this thing only has a value when r equals rm minus rn. Like the del, that's what del means. Right. So that means he can just port that into his argument and say, like, since this only has a value when r is this thing, then I can just use that thing in here and forget about the g of r. Right, which, so, I mean, it's kind of a common thing now to do, I guess, but basically at the time he invented it. You know, so the idea is like, since g of r is this del function, it's like an on-off switch. So it's 1 when this is true and it's 0 when that isn't true. Then I can just substitute that in for r. Then I just have this function, right, which is a double sum of an exponential. In the paper, he works out. Anyway, the double sum is going to be the same math as we used to solve this double sum thing. Like you just plug in the exponential thing instead of that, more or less. So anyway, so then the solution to it is this. Right, so that's the Debye scattering function. It's analytic. It's like a perfect function to describe what a Gaussian chain is. Right, so in order to solve it, he has to use like that this thing is NL squared. Like the distance thing is NL squared, then you just have N in here, then you can do the matrix stuff, just like in the race gyration. So this is only true for Gaussian chains, not expanded coil. Right, so this capital Q, so he throws in this capital Q. Capital Q means a lot of different things. So, but here it means this Q squared RG squared. He just substitutes that in. So it's been carried through that that's capital Q. It's the only place capital Q is used that way. But so you have that function. So let's see. And it's 1, is it 1 minus Q? It's Q minus. And then it's exponential minus Q. Translate it to that. Like that. Minus Q. Okay, that's good. So I'm going to go to that guy. So this is my shoddy writing of it, but if you're, so at low Q, then you can expand this thing into a series, right? So you can expand it 1 minus Q squared RG squared, and then plus 2 factorial Q4 RG4, then minus Q6, or let's see, this is squared. Q would be 6 RG6 over 6 and plus, right, but if it's small, you would only take usually the first two terms, but here he's got the first two here. So these cancel. Just -1 plus 1 minus that plus that. Then you just have these things, right? And then it's divided by, so it's got 2 Q squared RG squared squared. So it's 2 RG squared. And then, so this term's gone. Q4 RG4 is that term. So this guy's 1 over 2. The 2's there, so this is just 1. Sorry. So this is Q squared. This is Q4 RG4. This is that thing squared, and that's the first term that's left here. And the 2 cancels with 2, so you just have 1 for that. So that took me so long. Then you have minus, right? And you have Q4 RG4, Q6 RG6. That's Q squared RG squared. Then it's times 2 divided by 6 gives 3. And plus some other terms, right? And if Q RG squared is small, then that thing's exponential minus Q squared RG squared over 3. Because you first said it was small, so it's small here too. Okay, so it's small q, that's Green's law. Right, so that's good. I mean, it has to follow that. Every scattering function has to give you Green's law because that's the rule of how things work. So it has to be true. So I mean, it's true. So that's the low Q thing of this. Messy, but and then it's 2 over Q for RG4 times this mess, right? Q squared RG squared minus 1. So it looks messy, but it turns out to be like kind of a nice function. So then at high Q RG, then so exponential minus something as big is like 0. A really high Q, that just goes to 0. And then if this is large, it means it's larger than 1, so you just have that term. And then this thing cancels with this, so you end up with 2 over Q squared RG squared, which is that's our power law. So we have like Green's law, and then we have this -2 law where we have 2 over RG squared times Q to the -2. And so that's our power law prefactor. It's just kind of like 2 ways to get the raised gyration of this thing. There's a contrast factor in front of this. And so this I naught goes out in front, which is basically going to be like how many polymers in a thing, and then what's like the electron density of the polymer squared. So first, or the difference in electron density between the polymer and the solvent it's in, or if it was in a theta solvent. Right, so that thing works out pretty well. At high Q, it matches up the thing you want, and at low Q, it's Green's law. So you got everything you want from that function. So that's pretty good. Okay, so and it's analytically, you can derive it from basic facts, right? So you just say like it's Gaussian. So that anyway, so that's the Debye thing. It works. It's like well known to work and all. So there's also this thing though. So we got there's a twist to this thing, and you'll see this in papers. So you can, if you take Green's law, if you take 1 over Green's law, that's exponential minus plus Q squared RG squared over 3, and it's small q, then you have 1 plus Q squared RG squared over 3. Right? The exponential expansion, and then plus whatever. So forget about those. So it's at low Q. That's 1 over I. So then you could say, you could come up with a function I equals 1 over 1 plus q squared RG squared over 3 if you wanted to. Okay, and then you could say, forget about this, just say 1 over 1 plus q squared times some thing, okay, which came to be known as a correlation length. And that functions, so you have a prefactor 2 here. That function is called the Ornstein-Zernike function. Now, Ornstein, I think this appeared somewhere in history, but Zernike won the Nobel Prize, not for this. He won it for the confocal microscope. He was a Dutch guy. So Zernike is a well-accepted character. So is Ornstein. I don't know where Ornstein is or what he is, but Zernike is the microscope guy. Anyway, they proposed this function after Debye had derived the exact function, and then the nice thing, the bad thing about the Debye function is it can't be like transformed into a simple analytic function. Like if you do a Fourier transform works forward and backward. So if you do a backward Fourier transform of the Debye function, you can't do it. Like it's too complicated. But this is a pretty simple function, and it's a common one in Fourier. If you pick up a Fourier transform book. So that function, if you transform it, gives you this thing, which is surprising divided because this is an exponential decay function. So you think, and it's exactly the same. In fact, this is the same function as the Debye screening length function, what he uses for the charge thing for Debye screening length. Anyway, so this is so Ornstein-Zernike didn't propose this function, but people later on did. They said, oh, I can transform this, and they came up with this function. Okay, so it's got some problems if you think about it for a couple seconds, First off, when r is 0, it doesn't go to 1. It goes to like, well, who knows what it goes to when r is 0. I mean, it goes to infinity when r is 0. Okay, so it's not, so you could map out that function, okay, if you wanted to. And all right, supposedly this function, so I don't like this function. I should give you the disclaimer at the start, but so if you go to 0, that function goes to infinity. Okay, and it doesn't do it symmetrically. It does it like that. Because when it's negative r and positive r, it's got a different function because it's not squared. It's not r squared, it's r. Right. So the fact that it goes to infinity at 0 means it's not possible. The fact that it's not symmetric about 0 for a symmetric object, which a Polymer coil would be in space, means it's not possible either. Which means that the function itself is kind of nutty. Like, so this is going into like the realm of impossible correlation function, means this probably impossible scattering function too. But the thing has nice features, like it has Guinet's law, like it came from Guinet's law, so it's got Guinet's law. And if you go to high Q, well, Q times this thing is bigger than 1, so that gives you the minus Q minus 2 power law thing too. So it's got all the features you'd want out of a function if you're going to invent one for a Polymer coil. Problem is, like, it doesn't make any sense, right? And when Ornstein-Zernike, so they put this out as a footnote in a paper about a completely different subject. It wasn't in the paper, it was like in a footnote. And then in the footnote, they say that it should never be used. Like, it's just like interesting that it kind of looks like it. It kind of is how they introduce this. So nonetheless, this Ornstein-Zernike function has become like one of the main functions in scattering for polymers. So you'll see it in all kinds of papers, right? So just saying. Yeah. And also, if you did this, so you can do the same extrapolation. You can find out what the limits are for the power law prefactor. You can find out the what the race gyration equal to. So what you find out is that at high Q, then RG, because from the Debye function, which is exact, you can get what the power law prefactor is, and you can get, well, you have race gyration, right? But But if you translate it to the Ornstein-Zernicke and take the limits, you find out that these things don't equal. So you'd say that RG squared is twice this correlation length squared. But if you go to the Guinier part, you find out that 3 times that is the RG squared. So the two parts don't agree with each other. The two limits don't work out, right? So not in comparison to the exact function that's true. So that was bad, but that wasn't bad enough, right? So later on, Beaucage was like a postdoc for Debye at Cornell, and they came up with this function because they had, all right, so this is kind of like a trip down memory lane and scattering, which may or may not be of any value to you. So if you have a surface, say you have a surface, right? And then you say, so we have this vector R that we got from the correlation thing, you know, from the interference pattern. There's a vector R that comes out of the spacing of those interference things, the real space vector R. So if you have a surface, you could say that this surface could be covered with, and in the middle, so if you're in the middle of the material, if you have interference between these two, it's constructive. There's always one in the middle that's destructive because it's half the distance. So it's half the R. That means that the waves that come from this will be destructive from the two that interfere that come from these. Right, so half the distance gives you total destructive, in phase gives you total constructive. So the bulk of an object is going to give you 0 scattering because it will always have something to destroy the other. So the only place where you get contrast is at the surface, right? So that's called surface scattering. And it's got the behavior that the intensity goes with Q to the -4, which is kind of odd. This isn't like 3, it would be 3V, but this is 4. So anyway, you can find that if you say like the surface is made up of spheres of size R. On the surface, so you have that the intensity is going to be how many, and then the contrast squared. The contrast is going to be the volume of that thing squared. So like so this thing's going to be like the size of that, the small r cubed, and it's squared, so it's 6. And then this thing, how many of those is going to be 1 over the surface area, which is r squared. So that gives you, so cubed squared gives you 6. The number on the surface gives you 2, so that gives you r to the 4. The transform of that is q to the -4. Like it's an inverse, like frequency goes with 1 over time kind of thing. So anyway, so you can just kind of construct that you would get this -4 power law. Okay, but the problem is, like you want to see, and then you have Guinier's law, same thing. So you have Guinier's law, everything works for that, and you have this -4 power law. But then, like, how do you fit those together? All right, so Beaucage and Debye came up with the grand idea, like you kind of have this thing floating around, and then, like you want something like that, so just say it's 4, you know, instead of 2, and then you have power 4 at high Q, and you have kind of something weird at low Q. It's not Guinier's law, but it kind of looks like it, and you can use it to fit things. So it's called the Debye-Beaucage function. Also popular, not as popular as Ornstein-Zernicke, but still popular. This has obvious problems. It doesn't give you Guinier's law. It gives you something that kind of looks like Guinier's law squared, which the square of a Gaussian kind of looks like a Gaussian, more or less. So it doesn't exactly work, but it's better than nothing, you know. So people use this to describe things like coal dust and things. You get solid particles. You want to get the surface area. They use this function. Right. So that was bad. This was bad. This was a little bit worse. Right. It also has exactly the same problem. It's got this like asymmetric dependence in space and something that's random. Then there's so you can find all these in like papers published this year, you know. That's why I'm bringing it up. So Tübner-Stray is a really popular function, which is the same kind of function, right? So it also can be transformed. So this would be the correlation function for Tübner-Stray, and this is the function itself. So this is a really weird function. They never said anything about this is real. They just said like, we have this problem. They like,
Just like they combine it
Oh.
into equations.
yeah, all right. So this is really how things happen. Yeah. if you advertise it in the right way, it can, anyway. So they have this thing, it's for micelles. Okay, and micelles correlate with each other because they have some kind of charge on the surface. You get this kind of correlated structure. So that means you get a peak in scattering, but it's disordered, so it's like a pump. You know, it's going to be like -4 power law. Then it's going to be like a Guinet's law at some point. But you want to talk about how to fit that peak so you can get some kind of length, which they call the correlation length. Right, so you're going to get this correlation length out of this function. So they went back and like, oh, what can we do? What can we do? So I said, oh, like we got this function, that function, and just like get this function, right? And only way to get a peak is if make C2 negative and then C3 is positive, right? And those are called the Tubner-Stray constants, which have there's no physical meaning to them, right? You can fit things with a peak. Anyway, so you can transform that function and get this function. And then in the 1980s, guy at Argonne, Sinha, came up with this Simha, who's a guy at Case that did all the stuff on intrinsic viscosity. And then there's Sinha, who's at Argonne and came up with this scattering function. Both of them are famous. So anyway, the name's only slightly different. I don't know what the origin of those names are, but anyway, so Sinha said, like, so you can have things that are, so he has the Ornstein-Zernike that can kind of make this -2 thing, but what happens, like you get a good solvent and it's -5/3, or if you have like a fractal aggregate like dust, so you have dust, and you get -1.8 for diffusion limited aggregates. And so you can get, these are the fractal dimensions. So you want to have like some arbitrary like EF for this thing, right? So, so he also reached into the toolkit and found like, had this Ornstein-Zernike that seemed to be well accepted, then just like, oh, we'll stick with that and then we'll make it like divide by 2 and then have the fractal dimension here. And then that works out that he can get this DF out of the thing. And he worked out, well, I guess he started with this function. See, there it's known in the power law region that this thing would be R to the 3 minus DF. The transform of Q to the minus DF is this thing. The power law transforms to a power law for a transform. And then he used this thing and he called this a cutoff function. So here it was arbitrary, here it's arbitrary. So he introduces an arbitrary cutoff function. He was able to Fourier transform that whole thing and get this thing, right? Which follows, it does what it says it's going to do. It gives you this kind of Guinet law thing, gives you this power law, but it's so mixed up in like things that are wrong that it's kind of hard to see like the light at the end of the tunnel, you know? But this is also a popular function, you'll see. So it's a lot of garbage. It came out of like a footnote in the paper, you know? It's kind of funny how the one guy won the Nobel Prize, that footnote became like well accepted. So that's how things happen, I guess. It's kind of an interesting trail of tears here. So, all right, so that's it. That's my spiel on that business. This isn't really that relevant. Like I wouldn't expect you to, it's not well accepted, you know? So, I mean, I wouldn't expect that you would say like this thing's wrong because of that, but just keep in mind, in general, you're going to see equations that people are using, you know? So you have to know if it's a real equation or if it's something someone made up. Because people have written papers about the Tubner-Stray constants and how they change when you change the pH of a micelle, you know, and the numbers are like, don't mean anything, right? Like, in fact, the correlation length from either of these Ornstein-Zernike or Beaucage really are meaningless parameters. Like if you want to draw a cartoon of the structure, one time I used this Ornstein-Zernike when I PhD, and I went to give a talk at Kodak or something. And a guy said, like, what is the correlation length? You know, and in fact, the answer to that question is it's just a made up thing. It isn't anything. But I gave a pretty good explanation for what it was at the time. You know? But basically, since the function's bogus, then any number you get out of the function's bogus too. So you can't really stake too much on it. It might correlate with the size, you know, it could correlate with the size, but basically, I don't like the rate of gyration, but that depends on what part of the curve you fit, right? So anyway, so there's that, that's one part of this thing. Then the other thing, so we got, right, so last time I mentioned that when you go down to, this is the last thing in scattering, then we'll do like viscosity stuff. That's kind of technique on the things, but so we have IQ, and then we have this I naught thing. And so I'm gonna say it's -2. So we have threads, and you blow it up, you can see an individual thread, and then you zoom out and just see a dot. If you zoom out further, this thing becomes like uniform. Right, so uniform means that it's going to have like constant here, but there's still something causing that intensity. Otherwise, it would be like 0. Something is causing that flat scattering thing. So, so the simplest case is like you look at like a colloid, like you have polymer chains floating around a solution. And you say, well, if you plotted the density as a function of time or position, that it's not going to be the same density because these things will cluster because of KT, they'll like cluster together and move apart. Right. So the idea is that the basic idea of colloids is that you say that if you got rid of the solvent, these things are floating around in space, it'd be a gas. It'd be a gas, you would say like PV is nRT. You say it's got an ideal gas, or you could use the viral expansion if you want it for it. Right. So you say, instead of P, you call it the osmotic pressure, pi. And that's a number you can actually measure. Like you can build an osmometer, which is going to be a semi-permeable membrane. You have your stuff on one side and the solvent on the other. And the solvent like wants to dilute the stuff so that the pressure here is bigger than the pressure there. So that actually rises up, and pi is like the difference between those two. So you can build a little rig if you have a cellulose membrane, stick between two parts, and you just measure that pi. So that's like a real number, and it seems to follow with ideal gas law. You know, if you get the density, the concentration that you put in, and RT, that will give you that how high the liquid goes up. Right? Or you can do it if there's more than if there's binary interaction, then things you can add in the real coefficient, like rho squared, whatever. Right? So, oh yeah, that was one thing that group 2 or whatever did. That B, so when you have chi is A plus B over T, that's not the viral. In fact, B2 for polymer is a half minus chi. So anyway, that isn't the viral coefficient. That's just some letter B that they stuck in there. I mean, it's commonly called AB, but that's not the viral coefficient. But you might be able to work this out. Basically, they're 2 different things. Anyway, so we have these fluctuations, right? And that's what's given us the contrast. So you have like these 2 things gives you like delta rho squared, like the density difference squared. That's proportional to the intensity, I naught. So those fluctuations are what causes the I naught. If there were no fluctuations, you'd get no scatter intensity, right? And say KT goes up, then those fluctuations go up. Something's going to be proportional to KT. And so basically, there's something that has to do with how this pressure changes with the concentration. Like so you have the change in that pressure with respect to the concentration. It's called the osmotic compressibility. So you can imagine that number is kind of opposing this KT thing that's going on, so that building up pressure isn't a good thing. It wants to reduce the pressure. So things move around, they build up pressure, and then wants to release that pressure to go into the parts that are more dilute and have a lower pressure. Right. So this change in that thing with respect to concentration is what's deciding this delta rho squared thing. Right? So this osmotic compressibility is a thing that governs what that intensity is here. In fact, the bigger the osmotic compressibility, the smaller the intensity, because the more it pushes back, the less fluctuation you're going to have. Less fluctuation, less intensity. So it's inverse. So the intensity you see is going to be like 1 over this d pi d rho squared. It's a squared thing. It's the contrast between points. Right? It's going to be proportional to kT. The higher the temperature, the more the fluctuations. Then this osmotic compressibility is opposing the kT. That's how this thing works. So this I naught thing is really this osmotic compressibility. And if you can write that B2 is 1/2 minus chi, then you can write an expression for the osmotic compressibility in terms of chi, in fact, in terms of the free energy for the chain, so you can calculate what this I naught is in terms of chi. Right? Because this PV is the energy. We have an expression for the energy of the chain in the solution, the Floyd-Huggins equation. So you can calculate the osmotic compressibility, you calculate the I naught. So it's a way to measure chi. It's kind of a way to measure chi. So the details of it are kind of tedious, but that's the idea of it, right? So see if I can find this here. So it's right. This is kind of what that prefactor is from the osmotic. So you have 1 over I, because basically that's direct. 1 over is directly related to osmotic compressibility. It kind of makes it easier. So it's going to be the derivative of the free energy with respect to composition. Will give you this expression. That's the osmotic compressibility. And then the other part is Guinier's law. Like 1 over Guinier's law gives you this 1 plus, like the Ornstein-Zernicke thing upside down. Right? So that's kind of what. So that's called the Zim equation. Right? It's for low Q. It's for low Q RG, and then it's got this osmotic compressibility term. So you can determine at 0 concentration, you can get the molecular weight. From the dependence and concentration, you can get chi. So you put a polymer in solution, you make a bunch of different concentrations. You measure this light scattering as a function of angle. So this Q squared. Then if you extrapolate to low Q, you can get the slope will give you RG squared over 3, like the Guinier plot. And then if you extrapolate to 0 concentration, you can get the number average molecular weight, because this N is actually counting like how many are in there. It's not counting the mass of each. It's like how many dots are there in the thing when you go to I naught. So that gives you the number average molecular weight. And then so it's a colligative property you're measuring. And then this gives you the actually, it doesn't give you the number average. It gives you the weight average, because it ends up being the weight average. Sorry about that. This gives you the weight average. The osmosis thing gives you the number average. And then this gives you the chi if you get the slope and concentration. So you do a plot of concentration and Q squared and the intensity divided by concentrations, like this thing. Then you get points. You populate this with points at different angles, and then you can draw lines through the points for constant temperature and constant concentration and constant angle, and you can get these numbers from it. So it's kind of a complicated plot. Where this is used most now, you have a GPC. So you have a machine that'll separate out the components of the polymer, and then you run it through a light scattering at the end of that, and it doesn't kind of automatically does a Zim plot, spits out like RG, chi, and N. It's kind of automated, which is dangerous, but that's where it's mostly used now. There's a light scattering detector on a GPC, gel permeation chromatography. Anyway, so that's it. We're out of time. So let's see. So what else do I have? I cut it. Yeah, Monday I'll Zoom. I'll go through this end of this again a little bit, and then go to the viscosity thing. So hopefully that's okay. Then I'll find some paper for Friday. So, just any questions, anything, but. Okay. Hopefully, Mike, did you hear everything?
Yep.
All right, good. All right, I'll see you later.
Bye.